So, next we move on to the next module or next section on transforms. So, we will study 3 types of transforms. So, we will study actually we will first study probability generating functions, probability generating function or PGF. We have moment generating function, and we will study probably in most detail we will study the characteristic function. So, good references for this will be Grimmett and Sturzaker chapter 5 and OpenCourseWare lecture 14 and 17, lectures 14th and 17th, okay. And of course, I will upload notes, okay. So, these transform techniques are at some level you can think of them as some frequency domain techniques, just like in your signals and systems you have your time domain techniques, your frequency domain techniques. So, you can think of all your PDFs and PMFs as some kind of time domain functions and these transforms as some frequency domain functions, okay. So, that is a rough level of analogy. So, your knowledge of signals and systems will come in handy in this particular section, okay. So, this probability generating function which is commonly used for discrete random variables, particularly integer valued random variables. This is akin to your Z transform for your discrete time signals, right. And moment generating function is similar to Laplace transform, okay, and characteristic function is similar to Fourier transform, okay. In some rough sense we will see, okay, we will see properly. So, these transform techniques are very useful in a number of settings. So, sometimes they help one simple use is that sometimes they help you compute things much easier, right. Just like for example, if you have to convolve densities or convolve PMFs, it is much easier to go to the in your signal system you go to the frequency domain, multiply, invert your transform back, right. So, those sort of computationally they are useful, and they also are very useful in analyzing certain stochastic processes like branching processes, random walks. They are useful in proving limit theorems such as the central limit theorem, strong law of large numbers and so on, law of large numbers and so on, okay. So, they have a number of uses, okay. So, let us deal with probability generating functions. Let x be a x be an integer valued random variable, define gx of, so you can define the gx of z is equal to expectation of z power x. Okay, that is the definition of the probability generating function. Okay, so this is an integer valued random variable. So this is, you can just write this as sum over I z power I probability that x is equal to y. Okay. So z is just some parameter. Okay, you can think of z as, generally this z could be some complex number. Okay. So what you are looking at is some summation of a complex series. Okay, and this looks like, so if you were to look at this guy as some kind of a discrete time signal, this looks very much like your z transform, except usually you have a minus here for the z transform, but otherwise it is analogous at least. Okay, and you sum over all I. Okay. Now of course there is, when you write down a series like this, there will be all sorts of questions on whether the series converges, what kind of convergence does it, it is a complex series after all, right. So you have to talk about what the region of convergence is, whether does it converges absolutely uniformly and so on, right. So these convergence issues we will push under the rug a little bit for this course, okay, because it requires it requires some knowledge of complex analysis. Okay. You already know, I guess, that from your study of signals and systems, you know that Z transforms, the convergence regions are what kind of figures? They are generally annular, they are circles, right. In general, circles are annular regions. Then that is true here. Okay, it's there exists some radius of convergence. Okay. So let me just mention that. So convergence, so there exists R, so this could be possibly infinite, such that the PGF what I mean by PGF converges is that the series converges, right. This PGF converges for all Z such that absolute value of Z less than R and diverges for absolute Z greater than R. Okay. Actually, I think this particular statement is so I am missing out a little bit here. I think this statement is probably true for non-negative valued random variables, right. Otherwise you could have these z power minus I terms and you may have annular regions of convergence. So if this statement, I believe this statement, let me clarify this, but I think the statement is true for non-negative integer valued random variables, right. Let me clarify this once I confirm this. The one thing you can say for sure, so this R may be infinity also, in which means that the series converges in the whole complex plane. Okay. The one thing you can say for sure though is that this radius of convergence includes z equal to 1 for sure, right, because you will simply have. So, if you have z equals 1, right, or z absolute z is equal to 1, then you will certainly have absolute g z is equal to absolute value of that, which is less than or equal to absolute value of. So, you will just have 1, right. So, for z equal to 1 you have absolute convergence and therefore uniform convergence, right. So, this region of convergence will certainly include the unit circle, right, whatever else it includes or not, it does certainly include the unit circle, correct, this region of convergence. I mean normally if this were some arbitrary discrete time signal, that is not necessarily the case, but because this is a PMF, your region of convergence will include the unit circle, right. So, that much is clear, and whenever, so if you are in the region of convergence you will have absolute convergence and therefore uniform convergence, okay, and therefore this PGF will be well defined. So, and that is as much as I am going to say about convergence issues, okay. So, I mean I am not going to dwell on this too much because it's we are mostly going to use it as a tool rather than worry about its existence and so on, right, existence, analyticity, you can talk about all sorts of stuff for this complex function, but we will use it mostly as a computational tool, okay. So, I will not dwell on this convergence issues too much, okay. I will confirm this statement's correctness. I am pretty sure it holds for non-negative random variables. I will confirm this. So, let us do an example. Let probability of x is equal to I is equal to e power minus lambda power I by I factorial, I equal to 0. So, Poisson random variable, here your gx of z will be sum over I equals 0 to infinity right. And that is simply the series for e power lambda z, right. So, this will become e power lambda z minus 1, okay. And that is an analytic function in all of the complex plane, right, it converges uniformly, it is analytic in the whole complex plane, okay. So, this is for any z in C. On the other hand, if you try doing this for geometric, so if you have p x is equal to I is equal to 1 minus p power I minus 1 times p, then you will get g x of z is sum over I equals 1 through infinity 1 minus p z whole power I times p, isn't it. So, that is equal to p z over 1 minus z times, so sorry 1 minus p times z, and that holds for absolute value of z less than 1 over 1 minus p, correct. So, that is your radius of convergence or region of convergence. it clearly includes absolute z equal to 1, right, it always includes absolute z equal to 1, it is a little bit bigger than that and depends on p, okay, and out for z bigger than that it does not exist, okay. Is that okay? So, in terms of notation I am using big G for generating function, okay, and x I am suffixing it with the random variable I am talking about, okay, and z is the argument. So, let us look at some properties. First property is that if you take dg dz and evaluate it at z equal to 1, you get expectation of well, okay. So, the maybe the property 0 should be that gx of 1 is equal to property gx of 1 is equal to 1 always, right, you can see in these cases as well, right, gx of 1 is 1. I am saying that g prime of 1 is equal to the expectation of x. So, if you know the probability density function, you differentiate it with respect to z and set z equal to 1, you get the expectation of x. So, what is the reason that this is true? First of all, is does this derivative always exist? See, the region of convergence always includes, you see it always includes the circle, the unit this unit circle absolute z equal to 1, right. So, in that case you will have an analytic function which you can differentiate and you can just set z equal to 1, right. So, the way of proving this is that, so you are differentiating this, right, you are differentiating this series essentially and you will get I z power I minus 1, right, and you are setting z equal to 1, right, and you get I times px equal to I. So, which is the expectation, right. The only thing that I mean again I am not being very precise about is that how you can take the derivative inside the summation and things like that, right. If it is a finite summation you can do it, but so basically you are, it is justified when the summation converges to an analytic function, then you can take the derivative inside the sum, okay. I am just pushing those details under the rug a little bit, okay. And you can show that the kth derivative, similarly you can show that the kth derivative at z equal to 1 will give you expectation of x times x minus 1 times x minus k plus 1, right. Similar argument you can prove that, okay. Similarly, analyticity at, and if analyticity on the unit circle will imply this result, right. Third, if x and y are independent and z equal to x plus y, then g z Well, okay, so now I have to be careful. So let me call this something else then, right? X plus y is equal to some other random variable. What shall I call it? Or let me just call it z and just call gz of s, let us say, right. So, I mean I do not want confusion between the argument and the random variable. Gz of s is equal to g x of s times g y of s. Okay, so you can multiply the, so if x and y are independent, z is the sum of the two, just like so if x and y are independent, then you will the discrete random variables. So, you will convolve their PMFs, but convolving your PMFs is same as multiplying your PGFs, just like in your discrete, if you have discrete time signals that are convolving, you multiply the Z transforms, right. This is the same result. I am writing S here just to avoid confusion with the random variable itself, and the region of convergence will be the region where both converge, intersection of the regions of the convergence. So, if you want to show that sum of two Poisson random variables is independent Poisson random variables is a Poisson random variable, you can just directly look at this, right. If one of them has parameter lambda, the other has parameters mu, then you can show that the product will have parameter lambda plus mu. So, it is a Poisson with parameter lambda plus mu. So, in one shot you will get it without convolving and whatever, right. You get it? And obviously this extends to n independent random variables also, you just multiply the PGFs. So, if you want to find the PGF of a binomial random variable, you can take the essentially take the nth power of the Bernoulli PGF, right, because binomial is sum of Bernoullis, right. Yeah, so this is very useful. Okay, so we in your last quiz you had this problem on the negative binomial, right. So, try as an exercise, perhaps you want to try finding the PGF of the negative binomial and then proving that the sum of those two negative binomials is another negative binomial, right. That is something you proved the hard way, I guess, but you can prove it easier using PGFs. Okay. So, the last property I will talk about here, property number 4, is about a random sum of, so let us say z is equal to sum over I equals 1 through n xi, right, where xi's are IID discrete random variables, actually positive integer valued random variables, let us say, and n is independent of xi's. So, in this case you can show that gz of s, you can denote by zn, z big N if you like. Okay. So, gz of s is equal to Gn of Gx of S. Okay, so if you want to find the PGF of this random sum of random variables, right? So you compose the PGF of n and the PGF of S. Okay, And how do you prove that? You use iterated expectations. Okay, so you have gz of s is equal to expectation of s power z, right. That is, you write this as expectation of s power z given n. Okay. This is by iterated expectations, right. And so if you fix an n, so you can compute this, right, expectation of s power z given n. So if you are fixing an n, expectation of s power z will simply be the n time product of gx, right, because if you fix n equal to little n, this will simply become I is equal to 1 to little n xi, and the PGF of that we know, it's simply gx of s raised to the nth power, right. So but if you replace small n with capital N, this will simply become expectation of gx of s power big N, no, right, I am skipping a step, okay, and this looks like what you want, right, this is simply gn of gx of s. Okay. You have to be careful with the region of convergence. Okay. So, for example, you can now, if you are summing, let us say a geometric number of geometric random variables, let us say xi is a geometric with parameter p, n is geometric with parameter q. Okay. You go ahead and as an exercise you can try. You can try finding the distribution of z. Okay, if xi is a geometric with parameter p, n is geometric with parameter q, they are all independent. Okay, try this exercise. Okay, using this. Let's stop here.